So today I want to start discussing the proof of the theorem with Antonio Laface, Jenia, Tevelev, and Luca Ugaglia. Namely that in any characteristic, the effective cone of the moduli space M0 and bar, stable rational curves with n mark points, is not polyhedral if n is at least 10. And so let me recall that this also implies that in the same range, this is not a Mori dream space. And so without giving the definition, also let me recall that that Mori dream space does imply that all divisors which intersect curves non-negatively have a multiple which is base 0.3. So NF divisor is the same as a semi-ample divisor. So you can check numerically if something is semi-ample. And then all the cones divisors or curves are polyhedral, and so their extreme arrays and faces are geometrically meaningful for the maps, vibrations or maps that this variety has. And by Biekar-Kashini, Heiken, and McKernan, all varieties of Fano type are Mori dream spaces. So in particular, Fano varieties, in particular, toric varieties. Okay, so the idea here is to try to simplify the space and reduce to simpler spaces, the same kind of questions. So let me make a definition. Let's say I have two projective varieties, normal Q factorial. So every Veil divisor has a multiple, which is a Cartier divisor. And so I will call a rational map between x and y to be a rational contraction. So this is an ad hoc definition. There are different definitions in the literature. If this is a composition of two types of maps. So so either, and you can have several of them. Yeah? So either surjective morphism, so always between projective Q factorial varieties, or you can also allow isomorphisms in codimension 1. Yeah? So small modifications. So again, always Q factorial. Okay, and yeah, so it just means here it's an isomorphism in codimension 1. There is an open set with a complement of codimension at least 2, both sides, where the map is an isomorphism. And so then the remark, which is putting together results of several different people, is that rational contractions will preserve the properties that we're interested in. So in particular, if the effective cone of X is polyhedral, then the effective cone of Y is polyhedral. And then the same is true for Mori dream spaces. I just mentioned it because it's nice, but yeah, we're interested in this right now. And so, yeah, so I will be interested. I'm interested in, let's say, in the first property. So let me just say why this is true. So here, yeah, we need to check this property for these two types of maps. And for small modifications, this is immediate. Yeah, because you just take images because if you have an isomorphism in codimension 1, then divisors will intersect an open set where the map is defined. And so this is immediate, that the two cones are can be identified by taking images and closure. And then for the second one, so for surjective morphisms, this is not clear a priori, because when you push forward divisors in general, the push forward could be 0 if the dimension drops. And so, so there you can use a theorem of Buxom, Demaille, Paun, and Peternel. So their theorem is over C, but it was adapted in all characteristics by Fulger and Lehmann. And so it's the statement that you can look at the effective cone as the dual of the cone of movable curves, which I'll define this way. So again, we take the closure of the cone generated by classes of movable curves, again in the Néron-Severi space. So movable curve is something that there is an irreducible family of such curves that cover an open set in the variety. Sorry. And so then, for example, Fulger and Lehmann, they show that if you have a surjective morphism, then the image of the movable cone of curves is the movable cone of curves. And so, so polyhedrality, the property of being polyhedral will be preserved. Okay, and so then going back now to the space we are interested in M0 M bar, let me recall the Kapranov description. So we're looking for now rational contractions of M0 M bar towards simpler spaces. And so there was this theorem of Kapranov that describes M0 M bar as an iterated blow-up of, so recall this was start with a projective space, a dimension n-3, then you blow up n-1 points, and then all the proper transforms of lines spanned by them, and all the proper transforms of all the planes, and all the way to codimension 2. Always, yeah. So you can. So the way I said this is you first do points, then lines, then planes. And okay. Okay. And now you can do this blow up now in different. You can arrive at the same space, also choosing a different order of in which you blow up these things. So, as I said, you can actually fix the points to be so up to the automorphisms of this projective space. You can fix the first n-2 points to be just points where one coordinate is non-zero, and then the last one is all coordinates 1. And now there is you can notice that up to here, these are actually the torus invariant points of a projective space. And in fact, so when you blow up a toric variety along torus invariant points, well, you still get the toric variety. And if you keep blowing up torus invariant strata, this remains toric. So the space that is close to M0 M bar and it is toric is what is called the Lossev-Manin moduli space. Which is exactly the same, so I'll call this L and M, which is exactly the same blow up, but with 1 point less. Yeah, so again, you're blowing up n minus 2 points and n minus 2 lines, n minus 2 plane, n minus 2 choose 2 lines, n minus 2 choose 3 planes, and so on. And so the Picard number is roughly half of the one of m0 m bar. Yeah, so here it was 2 to the n minus 1, and here it's half of that. And so actually, so Gibney, Keel, and Morrison, when they were discussing the F conjecture for m0 m bar, they said there is evidence for it because it's true on the Lossmannian space, which has roughly the same complexity. And so again, one more reason to think that there is a toric variety, that there is a toric resemblance. So as I said, when you do the blow up, start with a Pn minus 3 to arrive at m0 m bar, you can do the blow ups in different ways. And so one other possible way is to go through the Lossmannian space. And then, so we need to blow up one more point, then all the linear subspace is spanned by it. And now, I want to notice that the point that we have here is actually the identity of the open torus in projective space. Yeah, so this is toric, and you have the open torus inside Pn minus 3, and this point is exactly the identity of this. So Qn minus 1 is the identity of this torus. So you can blow up this point, and then again there is further blow-ups to do, which involve all the linear subspaces that involve this extra point. But now the point is these are all birational morphisms, smooth blow-ups. In particular, they are rational contractions. And in fact, let me just notice here that all these spaces are moduli spaces. So here I didn't say, but so there is a moduli space interpretation for this toric variety. And in fact, for all these varieties, so there is a notion of a weighted moduli space of, a moduli space of weighted stable rational curves, or in general, any genus. So what is again remarkable, so this is due to Hassett. So what is remarkable, in genus 0, you obtain always smooth projective moduli spaces representing this functor of families, associated to families of weighted stable curves. So here the stability is just adjusting, you have a set of weights which are rational, and some conditions that, so the weights, all weights 1 will give you m0 m bar, and then other weights will give you simpler moduli spaces. Some condition, okay, and so the A stability is just that. Yeah, so you have a pointed A-stable rational curve if and only if, well, by definition, that take the canonical of this curve weighted by the points. This still has positive degree on every component. So you change nothing on the locus of irreducible curves. So P1s with n distinct points will always be stable. And what you're changing is what kind of reducible components you allow. And it's always simpler than the trees that you get for m0 m bar. Okay, so let me just mention so there are two results about. So now we're looking at the Losse-Manin space blown up at a point. Okay, so this is so result with Jenia Tevelev since 2015. So one is that there is a rational contraction from a Losse-Manin space at dimension 1 higher at the identity point towards M0n. So now, combined with this fact, this basically says that the properties we're interested in are essentially equivalent to understanding them here on the blow up of this toric variety. And this is a natural map. Yeah, so it is the one that is compatible with the forgetful maps. So if you forget the marking, in fact, this map is also compatible with just a linear projection from the extra point. Okay, and then the second result is that that this space somehow sees all toric varieties if n is sufficiently large. So if you take any projective q factorial toric variety, then for n sufficiently large, there are rational contractions. So first you can do everything torically. And then you can also add up this extra point and blow it up. So again, E is always the identity of the open torus inside X. Okay. No, just 1 point. Sorry, where?
Just define an element here. Oh, you mean the element is still the same as over there? It's not
Yes. So I think, okay, you may have to take an n large, yes. So X, this depends on X. Yes. For any toric projective variety X, there is an n after which you can construct these things. Okay, let me just give an idea of the proof of this rough idea. The idea is that the Losse-Manin space is very symmetric. Yeah, so it has it's a toric variety associated to a permutahedron. So more explicitly, idea of proof for the second part. Okay, so we said this is a toric variety obtained from a projective space, blowing up its torus invariant points and all the torus invariant strata. So the lattice associated with this is the lattice of a projective space described torically. So that is, you have n minus 2 coordinate vectors and you set them to 0, because you set to 0 the sum. And then the rays of the fan are spanned by these vectors, and then you start taking subdivisions of the cones, and you do it all the way. So this is generated by all the possible sums for all the possible subsets. And so what you need to notice here is that if you for any ray, minus that is also a ray. Okay, and so then the point is that you can you can start projecting the rays of the Losse-Manin space, for example, by setting some of these rays equal to 0. And then because of the symmetry, if n is sufficiently large, at some point when you arrive at the lattice, the same rank as the dimension of your X, you will cover a large portion of lattice points in that lattice. And so if the rays of your toric variety X are among that set, that means you reached so you can do a star subdivision of the fan of your X to arrive at a toric variety which has exactly the rays that you projected. And then you can try to build up other toric varieties going from down up, so that you arrive again at a toric variety with the same rays as the Losse-Manin space, except now it's rewired. Its cones are rewired differently. So okay, so let me write maybe the lemma that just makes this precise. Okay, so this will sound technical, so I not prove it, but you have a surjective map of lattices. Such that the kernel is just one-dimensional, spanned by one vector, primitive vector. And I want to look at the ray spanned by this vector. Let me call this R0. And if you start with a set of rays in this vector space given by this lattice, such that both this ray and it minus it are among the rays of this set. Then let's assume that that there is a fan that has the rays given by the projection. So a complete simplicial fan with rays given by the image. And so these two rays will map to 0, so I ignore those. And then assume the corresponding toric variety, proper toric variety is also projective. Okay. Then you can construct a toric projective variety X with rays given by our initial set. Projective Q factorial toric variety. And such that now, so this surjective map, this induces a map on the open tori. So it will give a rational map on the open tori, but now I claim that we can construct this X such that, so pi, this map induces a surjective toric morphism. From X to X prime, And furthermore, when you look at the rational map between the corresponding blow-ups at the identity points, this is a rational contraction. So it can be decomposed as a small modification followed by a surjective morphism. Okay, so I'm saying now that if you start with the rays of the Loss-Riemannian space, you can project, for example, all the way to a lattice of rank 2, and then you will obtain some rays in that in the plane. And now, for any toric surface with some rays contained in that set, then you can take a blow up of the toric surface so that you add all the extra rays, and then you apply this lemma repeatedly to again arrive at your favorite, to obtain a rational contraction from the Loss-Riemannian space or its blow up at the identity point. Okay, so yes, we want to reduce to dimension 2. And so then again, in order to prove this, you need to understand the blow-ups of toric surfaces. So here the statement is that in all characteristics, and for different characteristics you may need to change the surface, there are toric surfaces P such that when you blow up the identity point, the effective cone is not finitely generated, it's not polyhedral. So the idea is that actually you can make blow-ups of toric surfaces at one point to be similar to, let's say, blow-ups of P2 at 9 points. So rational surfaces, but they can have complicated effective cones. So now let me go to the simpler part of my talk. So what surfaces do we know which have, let's say, rational surfaces do we know such that the effective cone is not polyhedral? So you can do this, as I said, blow up of P2 at 9 points, but you can do this in a more general setup. And so for reasons of also simplifying the calculations, but also to bound to have in mind this bound, it's very useful to allow singular surfaces. And so
you're proving the theorem over there?
So I'm saying that now, what with this result in mind, if you know this, you know this. At least for n sufficiently large. And okay, there are specific ways to get effective bounds here, like how you project makes a difference. There are peculiar ways to project in order to get to this bound, which are not the most intuitively clear. But I'm saying that right now, we know that for n sufficiently large, if I know this theorem, I know this. That this is not going to be polyhedral for n sufficiently large. So now I want to concentrate on this, and how do I know how to do that? I'm saying let's look at P2 blown up at 9 points, and how can we make this resemble that? Okay, so something we call these elliptic pairs. And so elliptic surfaces, as people know them, rational elliptic surfaces, as people know them, they will be a subclass here. And so let's, I'm going to call an elliptic pair the data of a rational surface and with, I said, some singularities with log terminal singularities. So this is a condition on the chain of curves that appear in the minimum resolution. And so, for example, chains of rational curves are allowed, and so those are the singularities that toric surfaces have. So in particular, toric surfaces will have this. And then I want a curve that is contained in the smooth locus, an irreducible curve with self-intersection 0 and arithmetic genus 1. So in most cases, this is a smooth elliptic curve, but you can allow that this is a nodal or a capital cubic in P2. Okay, so then the question about the polyhedrality of the effective cone will be related to some arithmetic of rational points on this elliptic curve. So again, an example here, the simplest example is if you take an irreducible cubic in P2 with some 9 smooth points, distinct. And then you take X to be the blow-up of P2 at these points. And C is the proper transform. So as you can see already here, you can allow the curve to move in a pencil or not. There is no condition on that. Okay. So just for clarity, the assumptions that we have here guarantee some of the nice facts we know in the smooth case for X, a smooth surface, rational surface with C smooth, let's say over the complex numbers, but everything turns out it still holds in the setup. Yeah, such a surface will be Q factorial with rational singularities. So you do know that the H1 and H2 of the structure sheaf of X vanish. So the Picard group with rational coefficients is the same as Néron-Severi. So this is now numerical equivalence with rational coefficients. Adjunction holds. And moreover, this divisor, this has one section. So again, this is by just looking at the restriction to C and using adjunction, and the fact that K has no sections.
And right assumptions, I mean, assumptions imply.
I'm saying, the assumptions imply that. Yes, I claim this is true. In this generality, in any characteristic. So for the last statement, I'm just saying that. Okay. All right. Okay, so I'm going to look now at the subgroup in the divisor class group of divisor classes that, so now veil divisors modulo linear equivalence such that intersect C in 0. So this is a subgroup here. So note there that C and K have this property. And I want to look at the restriction map. This is some notation. I want to call and look at the restriction map of divisors that intersect C in 0 to a group of line bundles on C of degree 0. So C is contained in the smooth locus. So this is really a line bundle. And I want to call the order of the elliptic pair to be the order of C when you restrict it to itself. Okay, and so a remark here, if C and X are defined over a field that's not necessarily algebraically closed, the restriction of C, this line bundle, is also defined over the same field. And so I obtain then a rational point of the this elliptic curve if I identify this with rational points of C, assuming I have already one point. So in particular, if your field is finite, this order is always finite. And so okay, no, let me just say that. So then, I'm saying there are two possibilities now here. Either this order is finite, or it's not. And in the infinite case, assuming the Picard number of the surface is at least 3, this will be enough to guarantee that that the effective cone is not polyhedral. Yes, I'm saying there's a simple lemma. It's that there are two possibilities. So let me call E the order of some elliptic pair. So either this is infinite, and in this case, no multiple of this curve on the surface will move, or it's finite, and in that case, the order gives you an elliptic pencil. This is a base point free pencil. Yes, it's a pencil. So again, the proof is just using like standard sequences that use the restriction to C. Yeah, so if I look at this line bundle, this is a degree 0 line bundle. And so, yeah, by Riemann-Roch, you know that H0 is the same as H1. And then the line bundle is trivial if and only if this number here is 1. Or, yeah, so that is not trivial if and only if these are both 0. Okay, so I'm saying that this actually characterizes the order as being the smallest integer for which the smallest integer n for which this line bundle has sections, has at least 2 sections. Okay. Yeah, so I'm saying that this proves that E is the smallest n. And so in the first case, then you can already notice that. So you have a curve that is an irreducible curve with self-intersection 0. So C is an F class, and it does not move, so it's not semi-ample. And then, so there's an argument that goes back to Nikulin to prove that when the when the Picard number, when you add this as an assumption, the Picard number of x is at least 3. In the case of infinite order, so when this curve does not move, the cone cannot be polyhedral. This is the theorem essentially due to Nikulin. But if you have an elliptic pair with infinite order, yes, if the Picard number is 2, then it's always polyhedral, yeah, but this is not polyhedral. Okay, so I think I still have 4 minutes. So maybe I will give this proof for just being explicit. Okay, so let's you can always fix a basis for the Néron-Savary space. Yeah, so this is the Picard number. Let's say with rational coefficients, yeah, so such that the intersection form has so if I have when I take the self-intersection of a class, I get the simplest possible expression coming from, the signature is 1, r minus 1. R is the Picard number. I may assume also that the first, this divisor d1 is ample. And so then consider what's called the light cone. So this is classes with the positive self-intersection, non-negative self-intersection, which intersect this ample class non-negatively. Yeah, so explicitly, here this is okay, and so then so if the Picard number is at least 3, then the light cone is round. Yeah, so rho r is so you have, if you take a cross-section of the cone with a hyperplane where you keep the first coordinate fixed, you get really a round, a disk. Okay, and so then we can also see that by Riemann-Roch, this cone is always contained in the effective cone. Yes, you can prove the interior of this cone is, if I take a divisor class with square positive, yes, if I take a Cartier divisor D with positive self-intersection, which intersects an ample divisor positively also, you can see that that there will be sections if M is sufficiently large. And then the statement is how can you contain in a polyhedral cone this round cone? So, and the observation is that if the cone is polyhedral, then the classes, the extreme arrays, will have to be outside this cone. So there are classes with a strictly negative intersection. So all extreme arrays are generated by classes such that the self-intersection is strictly negative. Then you can prove that this has to be the class of a curve. An irreducible curve. And then notice that if this is a polyhedral cone, that means every curve will have a multiple which is an effective combination of these negative curves. So the second observation is our curve C is an F curve class with self-intersection 0. So I'm saying that such a class has to always be in the interior of in the relative interior of a maximal face. Yes, I'm saying that, for example, you can, so your curve is somewhere here. And then if you want, you can cut everything with a plane, a general plane that contains this class. The intersection, yes, so that's just an honest plane that contains the curve. Then the intersection with the effective cone will be a polyhedral, will be a polygon in this plane. And the intersection with this round cone is a disk. So, yes, I have this disk, and I have to contain it in a polygon. So this curve here, this curve class, you can. It has to be in the interior of an edge. So in particular, there is a way to write this as an effective combination of these negative curves. So that cannot happen if the curve does not move. Okay, so I'm going to stop here. But then the question will be how to construct toric surfaces that admit an elliptic pair structure. So you want to do the most natural thing possible. Just look for curves, elliptic curves, that appear in some canonical linear systems on a toric variety. And so that's what I'll do next time, and also discuss what happens if the order is finite. For example, if you work with toric surfaces, you can notice everything will be defined over the rational numbers, or you can also reduce modulo prime. And okay, so for all but finitely many prime, you can still have an elliptic pair. This time is defined over a finite field. So in that case, you cannot apply this Nikulin criterion because the order is the elliptic pair is always going to be finite. So in that case, you wanna decide also what happens when the order is finite, and there is an answer in that case also. So okay, so I'm going to stop here.
Thank you very much. So, are there questions? You need to use the mic. Katia? Speaking now. It's recorded.
So why cannot such a class be in the interior of the effective cone itself?
Right. So I'm saying, okay, you can always, if you cut this this space with a general plane, passing, let's say, through this point, the intersection with this polyhedral effective cone will be a plane. Will be a polyhedral again in the plane. Yeah, so it's a polygon. It defines a polygon in the plane. And I'm saying that now, and while the round cone will intersect it in a disk. I'm cutting, for example. Yeah, so I'm saying we fix some of these coordinates to be. So I said I take a cross section for a fixed x1, and then I also fix some of the other coordinates, and then I'm getting really honestly a disk.
That's exactly what is
yes, and so I'm saying now that
on the blackboard, but I don't understand why cannot this polyhedral cone be just much larger than the disk?
What do you mean? So okay. Much larger than it is.
Well, why the boundary of the disk cannot be in the interior of the cone?
It cannot be. No, I mean it's in this picture. Yes.
Sorry.
It's in.
Gamma is not big. Okay.
Right. So I'm saying that any Neff class with self-intersection 0.
Okay.
Will be on the boundary of this disk, yes, and so it cannot be a vertex here.
I probably missed the reason why gamma is not big.
Because I'm assuming that I'm saying any Neff class. I want a Neff class that is. So the fact I'm saying it's a Neff class just because that means I'm also having the effective cone has to be on one side of this, but also I'm imposing that I'm on the boundary of the light cone. Yeah, so. I'm assuming self-intersection 0, which is the case for my curve. C squared is always 0 by assumption. So C squared is 0, C is Neff, and I'm saying now that this has to lie on this circle.
It is Neff, so if it was big, then it would have positive. Okay, I
yes.
see.
More questions? No? Okay, so thanks a lot again.
Okay.